I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on rotational inertia, also known as moment of inertia. It's how mass is distributed around a rotating object. All right, in this video, we're going to talk about rotational inertia. It's also known as moment of inertia, and it's how mass is distributed for rotating objects. So in Newton's second law for dynamics, we have a situation where we have a rod that's attached to a disk, and that disk is rotating. So we can see from the overhead view that the disk is rotating horizontally. So what we're going to do is we're just going to look specifically at the disk, and we're going to draw a force diagram for the disk. And we know that the only force that's acting on that disk is going to be that tension force that's pulling horizontally in the picture, but from the overhead view, it's pulling downward. So we're going to use this and we're going to derive an equation for what rotational inertia is. So we know that the tension force is equal to the mass times the tangential acceleration on the outermost edge of the disk. But we also know tangential acceleration is just the radius times the angular acceleration. Now we can also use torque. We know that torque is force times distance. So it's going to be that radius times the tension force. But we also know that the tension force is equal to mass times r times alpha, so we can substitute that in and simplify and get mr squared alpha. But now the problem we have is the mass is not all evenly distributed at the same radius. We can see that on each of these circles that the radius is smaller and smaller, but the mass is also going to be different. So each one of those concentric circles shows a different amount of mass at a different radius, and we could draw countless numbers of those circles to represent any countless numbers of mass at different radii. So what we're going to do to account for all of those individual masses at individual radii is we're just going to sum up all of those in terms of individual masses times the individual radii. So we end up with a net torque is equal to the sum of all the individual masses times the individual radii squared times the angular acceleration. Now, the angular acceleration is a constant, so I don't have to use the constant in the sum part, so I can take the constant out, divide by the constant, and I can get that the net torque divided by angular acceleration is equal to the sum of the individual masses times the individual radii squared. So that sum is showing how the mass is distributed around the center for that rotating object, so in this case the disk. And that is called the rotational inertia or moment of inertia. So our rotational inertia is just how the mass is distributed about a rotating object. In this case, we're talking about the center of the disk. So the rotational inertia is the distribution of mass around that center. So the symbol for rotational inertia is a capital I, and we're multiplying mass times radius squared, so our unit's going to be kilogram meter squared. Rotational inertia is the rotational equivalent of mass. Now, in a translational situation, if masses collide and stick together, we just add the two masses together to find the total mass. Well, the same thing works for rotational inertia. If two things collide and start to rotate and they stick together, we just have to add the two values of the rotational inertia together to find the total rotational inertia of that individual system. Rotational inertia also shows the resistance to change the angular velocity of an object. So the larger the rotational inertia, the harder or more difficult it is to change that angular velocity for that object. So let's look at an example. We're going to start with just some point masses. And the point mass, the rotational inertia equation, is I is equal to mr squared. So let's take a look at three different objects that are at three different radii and have three different masses. And what we're going to do is we're going to calculate the rotational inertia for each of those point masses. We're going to treat them as point masses. So we can substitute the masses and the radii in for each of the equations. And then we can solve for those rotational inertias. So we can see that all the rotational inertias have the same value. which means that if all three of these objects are rotating, that they all would require the same amount of torque to cause them to come to a stop or to speed them up because the rotational inertias are exactly the same. So let's look at some rotational inertia values for some other common objects. So we're going to start with some objects rotating around the center. So we can look at a disk or a cylinder. A disk is just a slice of a cylinder. So a disk that has or a cylinder that has a radius of r, the equation for the rotational inertia or moment of inertia is going to be I equals 1/2 mr squared. Now, if we look at a hoop, so a hoop like a hula hoop has a radius of r, all of the mass is concentrated at the same point from that radius. So it's going to have the same equation as a point mass is I is equal to mr squared. Now, a sphere, a solid sphere, like a bocce ball or a billiard ball, is going to have a rotational inertia in terms of its radius that's given to you. It's going to be 1I is equal to 2/5 mr squared. Now, if we look at something that's rotating around the end, so a rod, let's say a rod's rotating around the end, it has a length of L, that equation is going to be 1/3 ml squared. And if we look at a rod rotating around its center point, so if we look at that example, we know we can find the rotational inertia. It's given that I is equal to 1/12 ml squared. Now, these equations would have to be given to you because they're one, not on the AP Physics 1 formula sheet, and two, if you're asked to derive them, you require calculus, which this is not a calculus physics course. So let's find the rotational inertia for systems of objects. So we're going to look at rotational inertia for this object that has rigid rods that are massless, containing 4 point masses that are attached. And this is like a pinwheel. It's going to be rotating clockwise or counterclockwise around that center point. So some information we know is that the rods from mass to mass have a length of 1, which means from the center point, each mass is 0.5 meters from the center. We have the mass values, 1 kilogram all the way up through 4 kilogram. And as I said, we're going to treat these as point masses. So to find rotational inertia, we just add the values together. So the total rotational inertia is going to equal I1, which is the 1 kilogram mass, through I4, which is the 4 kilogram mass. Treating them as point masses, I is equal to mr squared. We substitute the equation in for I total is m1r1 squared all the way through m4r4 squared, the 1s through 4s representing the masses. We can substitute in the mass and radii. All the radii are the same for each of the masses, and we can calculate the individual rotational inertia of each object, then add them together, and we can get a total rotational inertia for this object rotating about the center point is 2.5 kilogram meter squared. Now, if it rotates about a different point, then it would have a different rotational inertia. So this is just for rotating about the center. So let's find it for another situation where we've got a rod. Given the mass and the length of the rod, it's free to rotate around its end, around that point of rotation, that pivot. And we got a point mass that is going to collide and stick together and cause it to rotate. And the question we want to answer is to calculate the rotational inertia of the rod point mass system. So the rotational inertia, first we're going to need to mark up our diagram with the masses and distances. And as we know that we can just take the two rotational inertia of each of the objects and add them together. So the rotational inertia of the rod plus the rotational inertia of the point mass. So we know that the rotational inertia of a rod is 1/3 ml squared, and the rotational inertia of a point mass is mr squared, where r for the point mass is going to be the same as the length of the rod. So we can substitute those values in, and then we can calculate the total rotational inertia of 0.03 kilogram meter squared. All right, so the parallel axis theorem, this topic goes a little bit beyond Physics 1, but I feel it's important to understand so that you understand that an object can have a different rotational inertia if it rotates around a different point. So this is used when objects are rotating not around the center. So the way that you would calculate the rotational inertia is You take the rotational inertia total is capital I. IC would represent the rotational inertia of the center of that object, so the equation that we went through before. The mass is the total mass of the object, and h is the distance from the rotational point to the center. So let's look at an example using the parallel axis theorem. So we've got a cylinder, and instead of rotating through the middle like we looked at before, it's rotating around its edge. So we look at our equation. We have I is equal to IC. So if it's rotating around its center, I is equal to 1/2 mr squared. But it's rotating around the edge, so it's like that cylinder is rotating around the edge and spinning. So we're going to have to add the mh squared term. So the r value is going to just be the distance from the center of rotation. So I can add the total mass times the r squared, and I can get that the rotational inertia of a rotating cylinder around its edge is I is equal to 3/2 mr squared. So this is an introduction to rotational inertia, or moment of inertia. I hope this was helpful, and I hope you have a great day and an even better tomorrow. If you found this video helpful, click the like button down below and subscribe to my channel, Happy Coaches, and follow me on Instagram and Twitter at Happy Coaches.